So good afternoon, everybody. We are the hands-on group 2. We have been working on cloudy emission lines under supervision of Patrice. He's not here today. And hello, Patrice. And actually, we divided into 3 small subgroups because we were developing 3 different small projects. So today we are gonna present 3 small projects, which we divided our presentation into. Really, basics of cloudy, whatever like we were able to actually understand in the days we had. So it's a microphysics code that is able actually to predict and define the structure of a cloud through its thermal ionization and chemical structure and definition. Most importantly is the fact that actually it can go to atomic and molecular scale through an accurate simulation of the physical processes. And actually, how does it work? Well, in a very easy way to describe it, at least like this is how we try to understand it, is actually able to do a step-by-step equation solving of photons traveling through a defined medium, actually kayaking through a defined medium, and those photons can get absorbed, transmitted, re-emitted, and this is how actually we retrieve by integration backward the functions that we want to use. The 2 main points for cloudy are definition of the radiation field and the interacting medium. So the radiation field can be defined through shape and intensity. This is like the first part of the examples we were like studying with the examples when we started like approaching to cloudy, and then of course interacting medium that like depends on what you're like aiming to get from cloudy. So you can have cooling and heating functions, and we are going to present of course like the cooling ones because we are focusing on the emission lines. Thank you. And that's the first project.
Okay, this is the first project. Okay, our task was to create a radial profile for several emission lines of atoms and molecules, of course, in a photodissociation region. And this is our result. Basically, we plotted the abundance of H plus, molecular hydrogen, C plus, and CO in function of the visual extinction, okay, on the x-axis, and also on the thickness. Okay, basically here you can see 2 fronts. The first one, which is the atomic hydrogen over H plus, and the second one, which is molecular hydrogen over H plus. And also at the end, you can see the molecularization of the carbon, because we went from C plus to CO. Moreover, as input in cloudy, we put the hydrogen density, the ionization parameter, and also the metallicity.
Okay, so to actually learn something from these results, we're comparing 2 observations. So we compared 2 observations of these 2 starburst galaxies. And in the graph, you can see the observed flux that we converted to luminosity divided by this luminosity that we got out of cloudy. And you can see that for most lines, it works well, pretty well, except for the nitrogen plus line, which is almost 4 orders of magnitude off, or more than 4 orders of magnitude off. We think this might be because both these galaxies are star forming, and we didn't put in the right parameters into cloudy. And this is actually something that would be very useful to play with, to learn more about these kind of galaxies.
Yeah, hi. So we have been playing with BPT diagrams of H2 regions here. So we have computed with cloudy the emission lines. We have taken the ratio and we have displayed them. So what we are doing here, we are varying 3 parameters: the number density of hydrogen, the ionization parameter, and the metallicity. Of course, we vary one and we fix the other ones to see what happens. So if you have a look at the green points, that is the metallicity. So basically, as the metallicity goes down, of course, you have less oxygen and less nitrogen. So the points towards the origin of the axis. And if you're actually able to look at the blue points there, they're near the green ones. So basically, you see that this is the changing density of hydrogen. Nothing seems to change very dramatically. This is because the quantities that we're plotting basically don't really, let's say, depend with the same relationship to the number density of hydrogen. So in the end, the ratio cancels the the two, it cancels this behavior. And then if you change the ionization parameter, which is in red, basically, the higher the ionization parameter, it means that you are able to ionize better your gas. So in the end, you will create more oxygen 3 and more nitrogen 3, but here we are actually plotting the nitrogen 2. So what happens in the end is that this is basically going up, increasing, and then going to the left. So this is what we found.
So we did the complementary approach to that, where we modeled line emission from AGN with Cloudy, and we put in different radiation fields in the form of different SEDs. On the right here, you can see an example of that, where essentially this delta parameter in the upper right corner determines this kind of slope in the middle. I'm not sure this is actually helping when I do this with my fingers, but yeah, you can see this. This is basically what's being changed, and that then changes the amount of ionizing photons of that energy. So that will introduce some variation. And additionally, we also varied the same parameters as the H2 region people, which is the ionization parameter, the metallicity, and the hydrogen density. So this is the result with the ionization parameter. So essentially the light colors here are lower ionization parameters, and then the dark green are the highest ionization parameters. And you can see essentially a similar trend as Vittorio was presenting, where the higher ionization parameter, the more of the higher ionization states your gas will be in. So that means more O3, and in comparison less N2, because instead the atoms are in the N2 plus state. And you can also see that most of the AGN points actually lie in the AGN defined region of the BPT, even though there may be slightly more offset towards low log N2 versus H alpha.
So for the next part, we tried to vary the metallicity, keeping the ionization parameter and the hydrogen density fixed to see how the metallicity affects the BPT diagram. So basically, this is the plot. I set the hydrogen density to 10 Q per cc and the ionization to -2. So initially, you can see that as metallicity, when metallicity is very low, when we increase metallicity, the O3 over H beta ratio rises. This is because as we are increasing metallicity, we have more O3 emissions. So this is quite expected. Next, when we go into this region with a bit higher metallicity, we can suddenly see that this monotonic increase of this ratio stops and it starts dropping again, which is because when metallicity is high, we have far more amount of cooling. So we do not have enough amount of collision excitations of O3s, and so this ratio starts to drop. But compared to observations, what we found is that there is a bit of offset between what we found and the actual observations. So I think this is firstly, when the metallicity is low, this is expected that it will not reach the region, but even at high metallicity, there is a bit of offset, and maybe with a bit better modeling of the abundance, it can be resolved, and it will be interesting to look at it.
Okay, so the last part of this talk is that we played with hydrogen density also. So here you can see the BPT diagram with some background observations. We didn't want to tell you nothing about that. And basically these colorful points over there, it's our 4 models of different AGNs, and we played with hydrogen density over here. So basically we took 1 particle per cubic centimeter up to 10 to 5 particles per cubic centimeter. And the good thing is that there is a paper that analyzed all this thing, and what they say in this paper, and and the results actually correlates with our plot, is that if we have low density regime, then there would be no effect on the BPT diagram. But if we go if we cross critical hydrogen density, then the collisional de-excitation process starts to dominate our at the AGN, and that's why you can see that at, for example, log of hydrogen density 5, we have a shift of points, while other points stay at the same position. So yeah, and some summary. So we learned we learned a bit about Cloudy. We only started our way with this package, and we understood some, let us say, capabilities of this package. So yeah, enjoy your summary.
For the Cloudy emission line group.
Thank you for the talk. I was wondering, in your BPT diagram, in the first part, what are the background gray colors? Because I can see it extends to -6 in the, not this one. I think the first time you show the BPT diagram.
This one? Or
No, I think that, yeah, that one, yeah.
that one. Okay. So
You mean what are the gray points?
Yeah,
Observations.
observations.
Yes. So basically, okay. So we took some observational points. I'm not super sure about the details of these observations, but you want to compare what you get from Cloudy, basically,
Yeah,
with what you observe. So
I'm surprised that extends to -6 in the nitrogen 2 and H alpha. Yeah.
it actually extends like to -7 or -8, but there are like fewer points.
These are galaxies, galaxies or
It
individual.
should be, but I can't tell you more details because I'm not sure about that. Sorry.
Just one more question. What is the geometry of the density profile? Is it a shell or?
So basically, okay. So basically, we're kind of modeling an H2 region with Cloudy. So what you actually say is like basically what is your star in the center, and then Cloudy computes. So it makes a lot of calculations, of course, radiative transfer chemistry models and so on in space. And then we define like the end of our H. So the H2 region for us spans from like basically the star or like a bit more far away, and then the ionization front, which you can basically describe as like some ratio of basically ionized hydrogen over atomic hydrogen that drops at a certain point. And you say, this is my ionization front and this is your region in Cloudy. Do you want to add something?
So if I'm not wrong, actually, we were using the default parameters for like when we run Cloudy, and we changed parameters that did not include the geometry. So it should be spherical.
Right, so it should be spherical. Yes. Right, okay.
Oh.
Okay, thank you.
Any other questions while group 3 come down?
I have a question because I might have missed it. I'm sure you mentioned that at least. I think in the previous slide, when you compare the luminosities that you get out of Cloudy, yeah, exactly. Why are they totally off? Why is that?
Yeah, that's a good question. We think it might be because those galaxies are starburst, and the parameters we put into Cloudy don't represent that very well. But to really know, we should do like Perry or parameters in the model. Then I can give you an answer, but not now. I'm sorry.
Awesome. Let's thank group 2 again.